Hi everyone, and today we're going to talk about differentials. Now we know what a derivative is, but what is a differential? So let me give you the definition. Well, just like I said before, we know if y equals f of x, so we have some function with respect to x, then its derivative y prime, which equals dy dx equals f prime of x, is the derivative. That's what we've been calling the derivative. But now let's define what a differential is. So a differential is defined to be dy, which equals f prime of x dx. In other words, instead of f prime of x, we'll write dy dx times dx. So you can kind of imagine, or at least memorize it this way, is that dy equals dy dx times dx. So in essence, the dx's are canceling out. That's how you could memorize it. That's not what's happening here. There's more to the story, but this is our definition that we're going to use. Let's do an example. This example says find the differential dy, and we're given that y equals the square root of x squared plus 1. Now recall the definition of the differential. Dy equals dy dx times dx. So first we're going to find dy dx, so the derivative. Now luckily we have y by itself, so we can just take the derivative like normal instead of using implicit differentiation. However, we had to use the chain rule. So the outside function is the square root, and then the inside function is x squared plus 1. So we have the square root, you can write it as that thing to the 1/2. So the chain rule says you take the derivative of the outside. So we got 1/2, you keep the inside the same, and then we have that to the negative 1/2, and then times the derivative of the inside. So we got 1. Let's clean up this negative exponent. So I'm going to bring it down to the denominator, and it becomes the square root down in the denominator. And then times the derivative of x squared plus 1, which is just 2x. We have the 2's cancel, and we're just left with x over the square root of x squared plus 1. Now that equals our derivative, but we're looking for the differential, so we just use the definition. Use our definition here. So we have dy, well, let's write so dy equals, just writing out the definition, the derivative times the differential dx. Dy dx we just found is x over the square root x squared plus 1 times dx. And that is our answer here. That is the differential. Okay, now that looks a little weird, so let's do a part B. So part B is going to be, suppose x equals 10 and our differential dx equals 0.1. Then find the differential dy. Let's write that down. Here it is written down. So we just have to use what we found before. So dy, where x equals 10 and dx equals 0.1. So substituting in, well, remember it was x over the square root of x squared plus 1 times our dx, and that was all we want to substitute in. X equals 10 and dx equals 0.1 now. So instead of x, we're putting a 10 over the square root of 10 squared plus 1 times 0.1. Okay, so 10 times 0.1 is just 1. And then in the bottom, we just have 1 over square root of 101. And this is our answer. This is what dy equals in this special instance. All right, so now I was hoping to give you some kind of a graph of what's going on, some picture, so you can imagine what these differentials are. So what are differentials? So here we have a graph of our function f of x. I'm going to focus on this one point. I'm going to call it x. So we have this point is x comma f of x. All right, now typically we look at the tangent line. So let's draw the tangent line here at x. So it looks something like this. Okay, now we know something about this tangent line. Let's focus in on these points. So we know something about this triangle. So we know the slope of the tangent line, slope of tangent line, equals the derivative of f at x. And we also have our notation dy dx. So in a sense, the rise is dy, and the run is dx. So this value right here is x plus dx. And these are our differentials. Okay, so that value is dy. All right, but now we also want to look at this point up here. So it's directly above. So we got x plus dx is the x value for this green point. And now I want to look at this value, this distance. Okay, that distance right there, we're going to call the change in y. So dy is really close to the change in y. However, it's a little off because the tangent line isn't exactly on f of x. Okay, so let's call this green point. We can figure out what it is. It's x plus dx, comma, f of x plus dx. Okay, so that y value right here is f of x plus dx. And then the y value at the black point, the original point, is just f of x. All right, so we can figure out what delta y is now. So we just do the top, so f of x plus dx minus the bottom value, which is f of x. So we have some value for delta y. We also know what dy is, our differential. Dy, just from our definition, is f prime of x times the differential dx. So you can see the point of this picture is that the change in y is approximately our differential dy. So if you want to predict, for instance, how many French fries to buy in the future, we could estimate it with dy, some actual value, and then delta y, the change in y, is the actual number of French fries that you did sell. So they're going to be approximately the same.